Welcome to the first lecture on rolling, torque and angular momentum, and in this lesson we will explore the idea of rolling, which, let me say, may seem a bit challenging at first, but with enough attention and some practice you will find it surprisingly straightforward and maybe even enjoyable. So consider an object that is undergoing rolling motion along a surface, which in simple English means it moves smoothly without slipping or sliding or bouncing on the surface. Now, if we zoom into one of the wheels that is rolling, we see that there are two types of motion that are key to this discussion. One is the center of the object that moves in a straight line parallel to the ground, and two, the rotation of all points of the wheel around this as the axis of rotation. And in this lesson, we will combine these two motions, that is translation and rotation, to make sense of the topic of rolling without slipping. And now to get a little more technical about what this term really means, we say that in rolling without slipping, there is no relative motion between the wheel and the surface at the contact point, quite the way we consider when studying friction. So let us say you are standing on a sidewalk observing a cycle wheel as it rolls along. Well, what you see is the center of the wheel move forward at a constant speed, and let us call it V center of mass. And the other point you should observe is point P on the road, where the wheel makes contact with the road surface. And this also moves forward at V center of mass. After all, it has to, if the entire wheel has to move forward as one single unit. Now, consider a time interval t in which you can see that both O and P move ahead by a distance s, and the rider can see the wheel rotate through an arc, and let us say the angle of movement is theta. And as a result, point P that was touching the road at t equal to 0 seconds should also have moved through an arc length s. Then simple geometry tells us that s is equal to theta r, where of course theta is in radians and r is the radius of the wheel. So now let us go ahead and differentiate this equation with respect to time t, and what we get is ds upon dt is equal to d theta upon dt into r. But then we know that linear speed of the center of the wheel is ds upon dt, and also the angular speed omega of the wheel about its center is d theta upon dt. And so we can rewrite this equation as v center of mass, that is this part, is equal to omega r. Now this relationship is very important because this ensures the condition for rolling without slipping. That is, if for a situation where an object is rolling and you're told that for this object the equation v center of mass is equal to omega r is true, you can safely say that the object is rolling without slipping. Or you can also say that there is no relative motion between the surface and the object. Or in simpler words, you could say there is no skidding. So consider another scenario of a racer accelerating from rest, where the driver steps hard on the accelerator that makes the rear tires spin very fast. And in this situation, the tangential velocity at the surface of the tire, that is omega r, is greater than the forward velocity of the car's center of mass. And this means the condition for rolling without slipping, that is this, is not true, as there is relative motion between the tires and the road surface. And you can see the evidence here, which is the smoke rising from the tires. Basically, the intense friction between the spinning tires and the road heats the rubber, causing it to burn and produce smoke, and this is a clear sign that the tires are slipping on the surface. So you see, this equation is a foundation for analyzing rolling motion. Okay, with this in the background, let us study the rotational motion and the translation motion of this wheel separately. So here, this image shows a wheel in pure translation, as if every point on the wheel is moving forward without any rotation, quite like a sliding box in which every particle moves with the same velocity. And this one is pure rotational motion. That is, it is not moving forward, but just rotating at the same place. Now, we know from our study of rotation that every point on the wheel rotates with an angular speed omega, simply because every point moves through the same angle in the same time. Also, every point on the wheel has a tangential velocity given by the formula omega r, which also happens to be the linear speed v center of mass we found earlier. Then if we combine these two figures, what we get is rolling motion of the wheel. And interestingly, you would see that when you combine these two motions, the part of the wheel at the bottom, that is P, is momentarily stationary, simply because these two vectors add up to give a net zero velocity here. And it makes sense if you consider the fact that if this point had a net velocity of its own, the tire would actually skid, creating skid marks on the road. That is, there would be relative motion and it would no more be rolling without slipping. Okay, now equally interesting is this part at the top, that is point T, that is moving at a speed of 2 times v center of mass, because here these two velocity vectors add up in the same direction, increasing the velocity. So this part is actually moving faster than any other part of the wheel. Now this might be a very surprising discovery. I would actually say quite magical. But you observe this time exposure of a rolling bicycle wheel, and it is quite observable that the wheel is moving faster here than the bottom, because you can see the spokes are quite blurred at the top than at the bottom. So in this lesson, we found that rolling motion is a wonderful interplay of forces, friction, and geometry that explains how a wheel turns, why rolling objects don't skid, and even why the top of a rolling wheel moves faster than its center. So with this foundation, we are ready to explore deeper ideas about torque, angular momentum, and how rolling objects behave in the real world.